Let's move to the final part of our syllabus and final time straining my voice as well. That is log transformation. Okay, so guys, don't feel that this is a complicated area because for the exam we are not going to be tested on proofs and all. We just need to know how to interpret this. So that's what Miss also expects from us. So we'll prepare for that. In that case, this is also very simple. Don't take it to your head and don't get stressed because yes, you can do this. And with this, we are done as well. So I'll come up to this point. That means you can definitely do this and finish this off. And yeah, with a teaspoon of motivation, we'll move on to the topic log transformation. So why do we apply log transformation? That is for variables which show a high variation. For example, now I'll let me take the example which is in the slide as well. Okay, so they are saying one person has an income of 100,000. Let's keep it as 10,000. Okay, that person has an income of 10,000. And we have another big fat person who is earning 1 million as income. Now, if A's income increases by another 10,000, it's gonna be a big thing for him because his income has doubled. But if B's income increases by 10,000, the same amount, we are considering the same amount, the absolute changes are the same. But however, this is just 10,000 is just 1% of B's income. Here 10,000 is the 100% of A's income, but 10,000 is just 1% of B's income. So in such cases, it's better to use something like log transformation where we can interpret the regression coefficients easily and with adding much more meaning by considering the percentage changes, that is the relative changes, without the absolute changes. Okay, so we apply log transformation, as I said before, to data or variables with high variation. Can we apply this to Z? If the data consists of negative values and 0, can we apply? No, that is because now you all know this, right? Log of 1 is equal to 0. So if 1 is equal to 0, anything less than 1, that means all the all the negative values and even 0, considering 0, doesn't have a log value. The minimum log value is 0 and that's for 1. So we can't apply log for negative values and 0. Log transformation cannot be applied if the data consists of 0 and negative values. Okay, keep this in mind. And there is quite a lot of explanation over here in the slides, but let me put it into a simple chart for your easy understanding, and I feel that's much more better and easy to grasp as well. Okay, now we have 4 types of regression. First one is what we call as level regression. The next one is linear log regression. Then log linear regression. And log regression. Okay, the first part of this name, it refers to the y variable, that is a dependent, and the second part refers to the x variable. So when I explain the first one, you'll be able to understand easily. In level regression, what we do is, if I write the equation, it is y equals beta naught plus beta 1 x. What we have learned so far, no change. That means we are considering the absolute changes. So how do we interpret the beta 1 over here? When when x increases by 1 unit, what will happen to y? It will increase by beta 1 unit. So I can write this down as 1 unit change in x will lead to beta 1 unit change in y. Let me give an example. So let's say y equals 50 plus 25x. Then I can say when x increases by 1 unit, y will increase by 25 units. As simple as that. Okay. The next one is where we say linear log. So the y variable is linear, same as before, but for the x variable, we are gonna apply log. Here we are gonna apply ln. So how is our equation gonna look like? Y equals beta naught plus beta 1 ln x. We are gonna apply log for the independent variable only. If so, how you interpret is 1 percentage change in x. Why are we saying percentage change? Because we are applying the log to x. Okay. So 1 percentage change in x, it will lead to beta 1 divided by 100 unit change in y. Let me explain with an example again. 50 plus 25 ln x. So here you can see we have applied log to the independent variable x. Therefore, we say an increase in x is a percentage change. We have not applied the log to y. Therefore, it's still gonna be a unit change, not a percentage change. That's clear, right? So x will have the percentage change and y will have the unit change. So in such cases, we have to, when interpreting the variable, we have to divide the beta 1 value by 100. So how do we say 1% change in x, 1% increase in x will cause 25 divided by 100, which is 0.25 unit change in y. Understood, guys? 0.25 unit change in y. Let's move on to the next one. Here log is being applied to the y variable. X is the same as before where we have the absolute change. So ln will apply to y. So y is equal to, is it like that? No, I'm going to apply ln. Equals beta naught plus beta 1 x. So here x is going to increase by unit change. Why? We are not applying log for it. So 1 unit change in x will lead to beta 1 into 100 percentage change in y. Why do we say like that? Because we are applying the log to y, not to x. So x will increase by 1 unit, and if that's the case, y will show an increase, a percentage increase by beta 1 into 100. So if I write the same example, y equals ln y equals 50 plus 25 x. So we can say 1 unit change in x will cause or will lead to an increase in y by 2500. How did I get this 2500? I had to multiply this 25 by 100. That's also done. Now you all would know how to do this log-log regression. So we are basically going to apply ln to both y and x variables. So we would write y equals beta naught plus beta 1 x, and we apply ln to both y and x. And how am I going to interpret this? 1, you all say whether it's a percentage change or unit change. Percentage change, that's good. Why? Because we are applying log to x. 1% change in x is gonna have or gonna create a beta 1, again percentage change in y. So when we basically apply log to both sides, then we are saying both x and y are increasing by a percentage change, increasing or decreasing, whatever. Obviously here, if you all have noticed, instead of change in x, I can write increase. If I, that's the usual way we say, no, instead of change I'll put it as increase as well. As simple as that comes. So when you all are given an equation, just look into where they have applied the ln function. Is it to the independent variable, that is x? If so, when you are interpreting, you have to divide beta by 100. If they have applied it only to y, ln y, then you have to multiply beta 1 by 100 when giving the interpretation. If they had applied ln to both sides, then you don't have to change anything. You say the percentage increase in x, 1% increase in x has caused a beta 1% increase or change in y. Okay. The most important thing which you have to know under log transformation is that the useful property of it. One is that I said before itself, variables with high variation, when there is a variation, when there is a wide variation in variables, then it's useful to consider the relative changes. Relative changes than the absolute changes. This is one useful property. Another one is that when your units of measurement changes, your slope coefficient will not change, but your intercept only will change. Let me explain that with an example. So we say when there's a change in the units of measurement, units of measurement, or we can say in the scale. For example, scale, why do I refer to a scale? Now if you're converting meters to kilometers, you simply multiply it by 1000, right? The change is applied to the scale. You're multiplying is where we say change in scale. Okay, your slope coefficient does not change, only your intercept changes. So if I give an example, y equals beta naught plus beta 1 ln x plus a error term. Okay, so here I'm saying y is a income, sorry, y is a expenditure and x is a income. Now let's say I want to write my income in the equation rounded up to rupees thousands. I want to round it off to thousands. Okay, so my new x star, I want it to be income rounded off to thousands. That means if I divide my x by 1000, I will get my x star. So in this equation over here, I'm gonna transform the equation, right? I want to put x star now. So let me write that first. Y equals beta naught plus beta 1 ln x. I want to make everything to thousands now, rounded up to thousands. So it's going to be my new equation. But instead of x star, I can write x over 1000, right? The rest is the same. Plus beta naught. Alright. Now we have learned that when there is something like this, in log, when there is a division, we can write it as a subtraction. So I can write it as beta 1 ln x minus beta 1 ln 1000. Yes. Okay. So now beta 1 ln 1000, this is a constant. So this will get added with this constant. So we can write beta naught minus beta 1 ln 1000 plus this one beta 1 ln x plus this. So only the slope coefficient has changed over here. But I'm sorry, intercept has changed over here. These two get added and the intercept changes, but the slope coefficient remains the same. That means even if we change the units of measurement, it is not gonna affect the slope coefficient. That is like a biggest advantage which we see in log transformation. Okay, so where do we apply this? The real term application, the log linear and linear log model, they say we use in growth rates. We have to focus on this log model. That is where we talk about elasticities. The application of log-log model regression. That is the Cobb-Douglas function. Alright, so the Cobb-Douglas function is given by y equals a capital to the power something and labor to the power beta, which we don't know. Okay, now if we are given a function like this, we have to find alpha and beta. Okay, but can we apply regression? Can't. Why is that? Because one of the assumptions which we have to take in regression is that it should be linear in parameters. So the model is not linear in parameters, therefore we can't apply. So without doing a regression, how can we find alpha and beta? We have to try a way and find out a way to make this function into a linear, function which is linear in parameters, right? So in order to do that, let's take ln on both sides. Ln on both sides. So when it's like a regression equation of a population, we have to put this as well. Okay, so if we take ln y equals a k l beta ei. Okay, so ln y is equal to ln a ln a plus, and we apply ln to this, we can bring alpha in front, alpha ln k plus beta ln l. Then if we apply ln to ei, so log apply to a, it's a constant, right? So we can write this as, these are the notations which they use, right? So we can write over here. Okay, now we have converted this to a model which is linear in parameters. So by applying regression, we can find alpha, we can find beta. What does this alpha refer to? It's the percentage increase in output because of a percentage, we can't always say it's an increase, right? Because of, so I'll write that again. Change in output because of a percentage increase in capital. And on the other hand, we have the percentage change in output because of a percentage increase in labor. Is this a multiple linear regression model? Yes. Therefore, we have to hold the other one, other variable constant. So since we are talking about capital over here, we should say holding labor constant. And since we are talking about labor over here, we have to say holding capital constant. So in case if this alpha was like 0.5, we say that the percentage change in our 1% increase in capital will cause a 0.5% increase in output. If this beta was 0.3, then we say 1% increase in labor has resulted in a 0.3% increase in output. Okay, that is how you interpret these values. So basically, as we have learnt in calculus, this shows the output elasticity of capital. Marginal productivity of capital. And this is the output elasticity of labor. Okay, guys. Now there is something like this. Based on the values which we get for alpha and beta, we can say something about the returns to scale. Returns to scale. So if alpha plus beta is equal to 1, this indicates a constant return to scale. And alpha plus beta is greater than 1, then there's an increasing return to scale. And if alpha plus beta is less than 1, then we are talking about decreasing returns to scale. Okay. So they might ask us to apply this and do a hypothesis testing to show whether alpha and beta, the values over here, this production function, results in a decreasing returns to scale or increasing returns to scale or anything like that. So let's try out a question like that, and yeah, let's finish this off. So I'm gonna apply the second method, that is the transforming the log method. Okay, so what is a hypothesis over here? H naught is alpha plus beta is equal to 1. I'm gonna check whether this production function or the economy, does the economy exhibit constant returns to scale. This is my question. So to check that, I'm going to put h naught alpha plus beta equals 1 and h1 is alpha plus beta not equal to 1. So when we do the transforming the log method, we put this equal to theta, right? Alpha plus beta. Why do we use this hypothesis? Because there are two coefficients which we don't know. There are multiple coefficients which we have to include in a single hypothesis. That is the fourth hypothesis which I told. First one was joint significance. Second, individual significance. Third was the portions where we use the partial F test. And fourth one is this, where we have more than one regression coefficient included in a hypothesis. Alright. So under the second method, first one was direct t-test. Second one is alpha plus beta. That is transforming the log method. We put it equal to theta. So we can say alpha is equal to theta minus b. So in my equation, let's say my equation looks like this. I haven't given the equation, right? This is the question which they have. This is the equation which they have given in the question. L1y. They don't have to give this. This is what we found, right? Before. Okay, so instead of alpha, I'm going to write down theta minus b. Instead of this, theta minus beta. And the rest is the same. ln k, beta, ln l, all these are the same. Okay, so let me solve this first. Simplify this. So theta into ln k is theta ln k. Then beta into ln k is minus beta ln k. And let me write the rest. Okay, now can you see these two are over here? They have a common term. Do they have a common term? I can take the beta out. So if I take beta out, I can say ln, this one, ln L minus ln K. Okay, and ln by equals ln A plus this plus this. Okay, now we have transformed our equation. After this, we have to apply the hypothesis. We have to transform the hypothesis as well. No, same, alpha plus beta now it's equal to theta. So we can say our hypothesis as h naught theta equals 1 and h1 where theta is not equal to 1. Then we apply the test statistic where we put the value of theta and the hypothesis value of theta is here 1. Then the standard error. I don't think that we'll be tested in this as well in much depth because of the same reason I told before, because there are much more things to be questioned. So if you all have a rough idea on this, that is very well enough in order to go for the exam. So with that, guys, we are coming to the end of regression. I hope that you all have understood. If not, please do get it clarified, asking from someone who knows this. Make sure that you are very thorough with the areas, like that interpretation part. Basically all the interpretations of the regression coefficient, then r square adjusted, how to do a t-test for slope, joint significance, partial f-test, then how to write down the hypothesis for all the hypothesis testings, the h naught null hypothesis, and basic theory like why, what happens when we include a dummy variable, like if the number of categories is 2, if we include 2 dummy variables, then we fall into a dummy variable trap, right? So you all must know those things. If that's okay, then we are okay in terms of regression, I feel. Don't stress too much. Also try to find patterns between, because it's the same thing which is like getting repeat now, t-test and all f-test. It's the same thing which we learned in the first half of the syllabus with small minute changes. So be mindful of those changes. Now degrees of freedom, the values are changing, so just small minute changes, but if you all know that, then fine, all good. So all the very best for your exams, guys. First itself we are dealing and finishing off with stats, then all good and done, right? So yeah, let's meet again in the next semester. All right, then bye.